record on this computer. Okay. We are recording now. We are going to finish friction today. But I really wanted you to try one question on your own because we were doing questions all together. I wanted you to try one question on all by yourselves. So two of you now, Hatvi and Kavindi, have done this question number 4. I'm thinking what to do. Can others quickly try it? Quickly try it. And then there is one last little bit about friction that we have to cover, like a theory part. And then we will do a couple of more questions and finish off friction today. And we are going to start connected particles next week. Okay. So this number 4, can you quickly copy the diagram? So what you have is a box on a horizontal ground here. And it's been pushed along a horizontal flow by a force of magnitude 50. It's pushed, right? Pushed this way. It's acted at an angle of 20. It's given in the diagram. There is friction. Coefficient of friction is given 0.3. Given that the speed of the block is constant, your friend is here, but yeah, I don't think I should know Putta. No, okay. Given that the speed of the block is constant, find the mass of the block. So the most important piece of information given here is that the speed of the block is constant. What does that tell you? You're applying one of Newton's laws of motion there to tackle this question. That information you have to use along with one of the Newton's laws of motion to get an idea about how the forces are acting on this object, about the equilibrium. If the object is moving at a constant speed, according to Newton's first law, you have to know that. Remember, the first law gives you a relationship between the resultant force acting on an object and the kind of motion it has. If you know the resultant force, if you just know whether the resultant force is 0 or not, that means whether the forces are balanced or not. If you know that, you can predict its motion, and vice versa. If you know the motion, you can predict or you can say something about the resultant force or whether the forces are balanced or not. So if now we know the motion, we can say something about the resultant force. If your object is moving at a constant speed, the resultant force has to be 0. The forces must be balanced. And you know that we apply this condition in two perpendicular. You can apply in any direction, but it's simple in questions to apply that condition vertically and horizontally. You separately consider vertical equilibrium and you separately consider horizontal equilibrium. In any direction that you can think of, the forces have to balance. That is, if the motion is either constant speed in a straight line or not moving. Okay, so this is first law. So that's a story behind, that's a theory behind this. And then we would have to apply conditions for equilibrium, that's all. And there is friction here. So this is a friction question. So I think you had enough time to look at the question. So if I now start it, so you would start with here's a free body force diagram. This is question number 4. If I think of the object as a point object, right? The forces are red pen. The first force that you, if you are not comfortable with me replacing the object with a dot, let us have the object. Now, the weight of the object or the mass of the object is not given, which means we are not going to need it. So if you feel the need to label it with something, Since since the value is not given, just use a symbol. If the mass is m, the weight would be mg, or you can just say w. But let's put m because I think so. We are taking let the mass be m. Okay, I'm taking that to be m. Then the weight of the object would be mg, and then I would have reaction force acting directly upwards. Those would be the first two to mark. And then you have this way, this force acting, that is 50 newtons with an angle of 20. Let me take this to be my, it's always convenient to consider your object as a point. So all your arrows pass through that point. If you draw a object with dimensions, length and breadth, your arrows would be passing all over the object. Make it just a point. And then, so it's moving this way, and you know how you mark the motion. If it is accelerating, you mark it with double arrows. If it is just moving at a constant speed, one arrow. That means constant speed. And then there has to be friction acting in what direction? In that direction, that way, right? Opposite to the motion. And how much is it? Mu r. Mu r, it's the maximum friction, which is mu r. I hope you know why it is maximum friction. Oh, we have to find the mass of the block. It's the mass that we have to find. So you have to take the mass as m. Okay, right. So this is an important step, that you take it to be m. Okay. So to start applying conditions for equilibrium. Let me write conditions for equilibrium. What do you mean by equilibrium here? Forces are in equilibrium. Forces are balanced. Resultant force is 0. All these mean the same thing. Conditions for equilibrium. And we apply these, apply conditions for equilibrium in vertical direction and in horizontal direction. If you do it vertically, before that, what do you do with the slant force? You split it into two components. So let me use, do I have a different color? Let me use black. So I'm going to replace this 50 newtons force. I'm going to throw it away and replace it by two components. Now you remember, it's acting this way, right? It's acting like that way onto the object. So when you split it like that, one force is in that direction and the other force is downwards. Okay. So I will mark it as the downward one. I will mark pointed out of the dot, and this I will mark pointing that way. Okay. So now it's replacing this. It's no more there then. So how much is the vertical component? 50. That is 20. So 50 sine 20. How much is the horizontal component? 50 cos 20. Okay, right. Now I have all my forces in the horizontal and vertical directions, so that it's easy for me to apply the conditions for equilibrium. So vertical equilibrium, total upward forces, upward is only R, is equal to total downward forces. That is mg plus 50 sine 20. Right, that's it. Now what are my unknowns here? M is unknown, R is unknown, right? Let's just keep them and let's apply our equations. And then in the horizontal direction, the total leftward forces, I'm showing you right, the total rightward forces must equal the total leftward forces, because it's all balanced. Up balances down, right balances left. So total rightward is only mu r. That's maximum friction. If you want, let me write it here. F max is mu r. Oh, I know mu, right? Mu was how much? 0.3. So this is 0.3 r. I could have straight away written like that. It's okay. That is equal to, what else is there? It's only equal to this. 50 cos 20, right? Here's my only unknown here. Mu r I can write as 0.3 r is equal to 50 cos 20, and I can easily find r from this. Once I have r from here, substitute it in the first equation and you can find m. Okay, so very simple. This was a simple question. Okay, now any questions from that? Anyone? Was it clear? Is everyone here today? Let me check. We have Bimandi, Hatfi, Joanne, Kavindi, Malit, Mihil, Nathan, and Umalia. Okay. So again, Rachel and Madara. Okay. And Dineth. Okay. Right. Though you can't walk like that. Okay. So she's crawling now. Yeah. Right. Was that clear? Was that clear? Yes or no, please? Quick, quick, quick.
Yes.
Oh, Dinette doesn't do mechanics. Thank you, Hatfi, for reminding that. Okay. Can I know the answer to M from either Hatfi or Kavindi, the two people who have done this? What's the answer you got for the mass? Was Dinette there yesterday for the P3 class? I don't think so. What's the mass answer? Hurry up, please.
Miss 13.9.
kg. Is that correct? Okay, so you find this, and then by substituting that in 1, you can get the answer to M. Okay, good, good, nice. Right, now we have to cover a little piece of theory related to friction, and with that, friction topic will be over. So go back to your note, and we are under the big topic friction. We are under the big topic forces and motion, forces and motion. In that we are under friction. Now under friction, so the big topic is friction here. Okay. This is, I can't give you a, I can't give you a topic for this. Let's leave a line for the topic. Now you have to tell me what topic we need to give. Now this is a creative task about creativity. Leave a line for the topic. You have to come up with, after I talk about what we are supposed to learn here, I want you to come up with the topic. Okay, so leave a line for the topic, right? Okay. Now here's the background for what we are going to learn now. This is related to friction. Say you have, this happens whenever you have this thing that we are going to see. It's a phenomenon. Let's say it's a phenomenon. Whenever you have an object kept on a slopey surface, a ramp or a slant surface. So let me take a slant surface. Okay. So slanted at a certain angle theta, and you have kept an object on this surface. Now, if the two surfaces are smooth, what would you expect this box? What would you expect to happen? So you take this smooth surface, which is slanted, and you take a smooth object and keep it on this. What do you expect to happen? What do you expect to happen? Whatever the angle here, even if it has this very Hatfi is saying, Yeah, only rough surfaces have friction. When I use the word smooth in physics or in mechanics, the word smooth is used to say that there is no friction. But in practice, there are no 100% frictionless surfaces. I can say something is smooth in real, day-to-day normal talking conversations. If I say this is smooth, that will still have some friction, right? But in mechanics and physics, the word smooth is reserved to be used to mean that there is no friction. So if I say that this is smooth in a context of a physics or a mechanics problem, what I mean is that no friction. Okay, so I take a smooth surface and keep a smooth object on it. If the surfaces are smooth, you're welcome, Hatvi. If the surfaces are smooth, even the angle is very little, small. When I keep it, this will slide down. What force is now? What force is moving it down? It will accelerate down. It will accelerate. Okay, let me. So if this is smooth, if the two surfaces that are in contact are smooth, however small this slopiness is, however small theta is, I have exaggerated and drawn like a very steep one, but even if however small it is, if you keep an object on it, it will start to accelerate down always. Due to what force? What's the resultant force that is pulling it down in this direction? What's the resultant force in this direction? Which force is responsible for that? Who's doing that? Very good, Mihail. It's not completely the weight. Can you make it more accurate, your answer, Mihail?
Gravity.
No. No. Now, other thing is, please wait. Can you please give your responses to everyone? Not just don't send them to me privately. Others have to know what. Now, I will tell you about how others are feeling. I'm like out of the blue. I just say something to someone because they are not seeing what you are telling me. So Mihil said wait. I said very good response, but make it precise. Hatvi says normal. That is normal. You mean normal reaction? Normal reaction is this way. It is perpendicular to the direction of the motion. This has no effect. This normal reaction has no effect to the motion. It's moving this way. And then Mihil changed to mass. Mass is wrong. Mass is not even a force. I'm disappointed in that. I'm asking what force is responsible of bringing this box down. Gravity is that's a bad. That again is not a good answer. Gravity means weight. Okay, gravitational force is the proper word. One more chance. Let me show you weight. Here's weight. Weight is acting this way. Ha, Malik, thank you. It's a component of weight. Who's pulling the block down? A component. Which component? The component that is parallel to the. You know that this can be replaced with two components. It's as if this weight acting vertically downward is as if you have two separate forces acting, one this way and one this way, as if. So you can completely forget the weight, which is actually acting completely vertically downwards. It has a part of its effect this way and part of its effect that way. So we can take those two components to represent the weight. And then this is the one, well, how much is that? W, the theta will be here, W sine theta. This is the force that is moving it down. There is no friction. So that's the only one single force acting in this direction. So it will accelerate down, right? So this is when the things are smooth. That's okay. If your surface is rough, now again the word rough is when it is used in a mechanics or a physics context, what we mean by that is there is friction. That's what we mean. You have a rough surface, that means it's a frictional surface. If you have a rough surface, sometimes it can be very noisy in my area. So if you're hearing a lot of like vehicle sounds. Excuse that. Okay, now let's consider. Again, I have exaggerated my slope. You won't have, even if you have very shallow slope, the earlier thing that would happen if it is frictionless, whatever the thing will slide down. Now you take a rough surface, some roughness. So there is a certain mu defined for it. There is a coefficient of friction defined for it. For the sander, you keep an object on it now. Okay, so there is a certain coefficient of friction defined for this the two surfaces. Okay, now what could happen? It's rough and you keep the box. What could happen? What could happen? What could happen? Earlier, if the surfaces were smooth, however small this angle theta is, your object is going to accelerate down. If the surface is rough, what could happen? What are possibilities? Mihiel says it could stick in one place. For that to happen, if that is a possibility, let's take one by one. Okay. So Mihiel said it could stay in one place. I'll just write stay in one place. Under what condition would it happen? It will stay in one place. What happens? What can you say about the forces then? And Malit says either the particle moves or it doesn't. So Malit also has this option. It doesn't. Hatvi says object can remain without moving. Same option. You all think then that on a rough surface, one thing that could happen is when you keep your object, I can show you that. If I take a bit of a rough, right? If I keep this, it could, I hope you see it. Do you see this? Do you see this? Right? It's not moving. Now it's moving. If I make it, when I make the angle more, I am increasing the component of weight acting down. Sin theta increases, right? But that's one option. It's not moving. What can you say about the forces? What's happening here? For it to carve in, this is balanced forces. So what are the forces acting here? Weight acting down. Let me mark the normal reaction also. Normal reaction acting up. And let me replace weight. I'm always using the black color when so I'm removing this. Okay, I'm replacing that with W cos theta and W sin theta. Right, and also, what else do I have here? Because this object is trying to move now. Friction acting in what direction?
Upwards.
Upwards. How do you know it's upwards?
Because it should move down.
Yeah, it's trying to slide down. The component of the weight. It's trying to pull it down. This is trying to pull it down. Then immediately friction will start to act upwards. And if it exactly balances W sine theta, it will not move, like you said, right? So I'm going to wait. So let me mark F. It could be F max, or it could be something smaller than F max. But if this would happen, if friction F, my simple F, when I write F like that, that represents friction. If F is equal to W sine theta, it will stay in one place, right? If this will happen, only if that will happen. This could even be F max. We don't know. Whatever it is, if the amount of friction balances out W sine theta exactly, your thing will not move. Suppose W sine theta is greater. Like now, it's greater. Suppose W sine theta is bigger than the maximum friction that the surface can apply on that, then what would happen? If your the downward component of the component of weight, if it is greater than even the maximum friction, something is stuck. Am I stuck, or is it only the document?
The document.
Let me try again. Okay, do you see it now?
Yes.
Right. Okay. So if I write the first scenario again, if W sine theta is equal to F, or it could be F or F max, who cares? But if whatever the friction you have, if this is exactly equal to that, this means it will stay in one place. It will stay in place. But if W sine, now remember W sine theta, uh, it can vary only when theta varies. By slanting it more or less, I can vary it like I did now. I can't change the W, then I have to change the object, right? One object, so one W. But then the component of the weight acting down, I can vary by varying theta. See? For a small theta, it doesn't move. When I increase the theta, the component starts increasing, and when it goes beyond the maximum friction, it will start sliding down. Make sense so far? Make sense so far?
Yes, ma'am.
Thank you. Okay, right. Okay, now, now, suppose this is your object. Okay, that's your slope. I'm going to put some values now. Suppose the component of the weight, is let me start with maximum friction. Suppose the maximum friction that can act between these two surfaces is 10. Okay, so friction will start, friction is able to start from 1 Newton, 2 Newton, 3 Newton, and go up to at most 10 Newtons. That's a maximum friction that can act. If the maximum friction that can act between two surfaces is 10, and according to this, the angle in the slope, if the component of the weight is, say, 15 Newtons, so that way 10. Okay, if this is 15 Newtons, what would happen to the object? If the component of weight is 15 and the maximum friction is 10, so this will stop at 10. In this scenario, what will happen? What is this? Component of weight. Oops, stuck again. What is this? Maximum. It doesn't let me try closing this and opening it again. Give me a moment. This is part of having to live with technology. Okay, it's not coming. It's working here. So these are the obstacles that we have to face. Okay, we are back with that now. Okay, don't get disturbed when these things happen, right? We have to be very patient and accept these things. We are doing all this with the help of technology. We are depending on it. So power can go off, my internet can drop, my IV can stop working. We have to find our way to do this this activity through all those obstacles. Okay. Okay. Is the screen bright enough? Let me know if anything is not clear. I mean the screen visual. Do you hear me? Hello? Yes, okay.
Yes.
Right. Here's the component of weight. I'm keeping the slope constant. So the component of the weight is not changing. It's fixed 15. Okay. There is no reason why it should change. So this is 15 sine theta. I did it in general here. W sine theta. W sine theta. Okay. And that I have taken a value for that now. Let it be 15 newtons, right? 15 newtons. And what is that? That is friction. And the object, here's the object. I have made it into a point object. If you don't like it, I can draw a box there. Right. Maximum friction is 10 and the component of weight is 15. If I keep an object on a surface for which the maximum friction is 10 and the component of the weight is 15, where the moment I keep it, what will happen is this will start to come down. So we all agree on that. Now, if I want to keep it still, now it's sliding down. If I want to keep it still, I would have to provide an additional force on it upwards. Do you agree? I have to apply an additional force upwards. How much do I need? How big a force? Good, Hati. How big a force do I need for this particular example to keep it from not moving? To keep it from moving, I'm going to draw that force with a special color. If I apply a force that way, is that color visible enough? No, it's not visible enough. Okay. In that direction, if I apply 5 newtons, it's an external force. Let me call it external force. I am pushing. Somebody externally has to come and do it. These are natural forces. They naturally occur. The earth does this, the surface does that. Nobody is doing it. It just naturally occurs. This 5 newtons, somebody has to come and push, give. Okay. So if you give 5 newtons, now what will happen? It will stay in place. Do you agree? I need a quick feedback. Do you agree? Or like if you have the slightest, okay, so you have to stay with me. If you feel like you get lost, you are lost or anything, you have to quickly stop me, okay, and tell me that you didn't understand from whatever the point onwards. Okay, now tell me, so for this scenario, the force that I need to apply on this object in order to keep it still is a 5 newtons force up the slope. Now tell me what will happen if I if I give 4, if I make this 4 newtons, what would happen? It would still come down because there is an unbalanced force of 1 newton downward. If I give 3, none of that is enough. Can I give 1 newton and keep it still? No. 2 newton, 3 newton, no, because I'm short of 5 upwards to make it balanced, right? Exactly 5 would make it balanced. My question is, if I make it 6 newtons or like more than 5, a little more than 5, say 6 newtons, I'll increase it by 1 each time. If I increase it by, let me draw the box for you. I think seeing the box might help. Here's 15, that's not changing. Here's the 10. I don't know, would 10 be there? I'm just drawing the 10. These 5 newtons, if I make it to 6, the moment when I do that, I don't know, would this 10 any longer be there? I don't know. Let me What would happen? What do you think? Did I make a mistake in the drawing? What I did was in this scenario, I changed my 5 to 6. What would happen? Malit says it goes up. Hatvi says it goes up. I'll wait for some more responses because that's not what will happen. Who can tell me? Hatvi is saying stay in one place. How would that happen? So what would happen? Now remember, this 15 can't change. Its direction can't change. Its size can't change. It's fixed. This arrow and the number 15 is fixed. No Sakkaraya can change it. Now I change my external force to 6. Remember, this friction is a fluid force. Remember, its direction can change. It opposes the motion. If you're moving this way, it'll act that way. If you're moving that way, it'll act this way. It's a fluid force. Its size can change. I hope you remember this. The maximum is 10, according to my example. What would happen if I make it, if I increase this to 6? Would this stay in 10? If it stays, how can it, okay. If it stays in 10, now you have 16 acting up and 15 acting down, and then it should move up. And if it is moving up, friction should act downwards. Do you see, you bite your own tail? It's like it doesn't work. You have marked it upward, but then having marked it upward, make the resultant, the total force acting upward 16, then it has to go up. But then if it is to go up, this 10 can't act. It has to act in the other direction. I mean, that's all messed up there. What happens here? This 10 won't stay at 10. Because now it's, think about it like this. In this scenario, again, this is tough. Okay. In this scenario, I am helping friction. I'm helping friction to keep it still. Friction was trying to keep it still, but it can't increase itself more than 10. So it can't keep the object still by itself. So I had to jump in and help friction. Think of friction as a friend, and you are helping him. He has come to his maximum. We can't push anymore that way. So you are providing 5. Now, if you provide 6, your friend can relax and what? It was pushing by with its maximum size 10. Remember, you can change, friction changes. Still, you can't think what will happen. It won't be 10 because it doesn't need to be 10 now. Remember, friction matches the scenario. It matches what's going on. When I try to push this table, when I try to push it with 1 Newton, friction starts to act in the opposite direction with 1. If I increase it to 2, friction increases to 2. Remember all this thing? Oh, Hatvi says it can be 1 Newton in the other direction. Then this would be 16 and I'm only putting 6. No, it won't. This friction will drop by 1. It will become 9. Because now I am helping friction more. You reduce your force. I will give that 6. Now together we have to give 15. It's like a contract, isn't it? This 15 force is trying to push it downwards. It's a constant force. And you and I together, who and I? Friction and I together has to counterbalance it. So when friction was at its maximum, I had to only give 5. Here's another possibility. I can give 6 and friction could be 9. I can be 7 and friction could be 8. Do you see? If I keep increasing my force, friction will reduce. because it's a fluid force. It only acts to the right amount to keep things from moving. Am I clear? There is more to the story. We are still halfway through. So far, is it clear? If I put 6, friction will drop to 9 and it can still stay in balance. Okay, Hatvi says it's clear. Thank you, Hatvi, for responding. I need you to respond quickly. Say yes or no. If you didn't understand, say no. Then, so this moment now, here's another way in which I can keep it good, Nathan. Keep it still. So this 50, this is always there. It's fixed. Okay, it's not going anywhere. That 15 acting downward is a constant force. It's the component of the weight that is just there. Then if I make it 6, if I change my force, friction will automatically change. Now you can't see what I have drawn. This is the thing. I don't know why that happens. Then friction could be 8. 8 and 7 together, still balancing this. 6 and 9 together, still balances this. Here, friction was at its max and I only needed to give 5. So this is the smallest force I need to give to in order to keep it stay still. What's the largest force? What's the largest force that I can apply, keeping this object stationary? Hatvi thinks 15. If I increase this to 15, I like this of Hatvi, okay? I drop to 6, friction goes 9. Sorry, friction drops to 7. Sorry, wait. This is me, this is friction. When friction was at its max, I only had to give you 5. If I increased mine, this was, so the total has to be 15. This would be 9. I increase by 1, this drops by 1. I increase by 1, this drops by 1. Right? Sorry, drops by, yeah, by 1. How far I can go? I can increase up to 15 and let friction relax completely. Friction doesn't need to push anymore. Okay? Okay. Now my question is, what is the largest force I can apply on this object so that it will stay at rest? Hatvi said 15. Good answer, but it's not 15. Now let me draw that 15 scenario. Here's the 15 scenario. If I go all the way up to 15, here's the 15. This way, I am giving 15. I am giving 15. Then friction, no friction, because it's not this, my 15 itself balances this, no friction, nothing, this is 0. Okay. If I go ahead one more step and make it 16, what will happen? If I increase to 16, what will happen? Now think before you say anything. Think and give an answer. Yes, the 15, constant 15, it never changes. It's there. It's always there. I change my force to 16. What happens? Okay, Kavindi says, friction starts acting from down. Friction will now flip the direction. If you look at my table, how I was, now what was happening to friction? Friction was relaxing itself. It started with the maximum 10, 9, 8, 7, 3, 2, 1, 0. And when I change this to 16, this would go to -1, which means, I mean, think about it. Look at this. Look at this. There is more force in that direction. The object will, it's like it will start, or it will try to move up. Friction will immediately come into the story and start now acting against me. Isn't it? Friction will start, what color do I use? Friction will start acting down. By how much? By how much? How much will it be? 1. It will fix at 1. If not, see how what a wonderful force this is. It changes its size and also the direction to match the situation. It matches in the sense it wants to keep things balanced. It will make it 1. I increase this to 17. Friction will go to 2. Now tell me, what's the maximum force I can apply and keep this object at at rest? How far can I go? Now, throughout now the object is not moving. At 5 it was not moving. 6, 7, 8, my external force, I keep increasing, it's still not moving. What's the maximum force under which I can keep it still? Think before you say. Very good, Kavindi, very good. I'm so happy. I don't know whether I spoiled it for the others by responding to Kavindi's answer. So Kavindi's answer is right. What do others think about this? Do you see that it is 25? Now friction can increase up to 10. So if I make this 17, friction would be 2. If I make it 18, friction would be 3. How far can it go like that? This can go only up to 10. So when I'm 25, it will be 25. And then if I increase it further, it will start moving. My question was, what is the largest force I can apply on it to keep it still? So it's 25. So the summary of what we just saw is this. When you have an object kept on a rough surface, by applying, if you keep it at rest by applying an external force, if you have to give an external force to keep it still, your force could be in a range. The size of your force can be in a range. There is a smallest value to a largest value that you can apply to keep it from moving. In the example I took, from 5 newtons to 25 newtons, if I applied any value force between those two numbers, I'm able to keep it still. Now if I show you the whole thing like at once in one screen, you can't see like everything, but that's a maximum I can make it small. If I want to draw this last diagram, this is 15. If I can make it 25, I can go all the way up to 25, and then friction would be 10, balancing. So for all these, this object is in balance. It stays still. Okay. So my applied force can go from 5 newtons to 25 newtons. Okay. For any value between 5 and 25, right? I can keep it still. Smallest is 5, largest is 25. The difference between this and this is this. When I'm applying the 5 newtons, okay, it's about to go down or up. It is about to go down or up. It's in limiting equilibrium. Whenever F max is, if whenever F max has been reached and your object is not yet moving, it's in limiting equilibrium. If you remember that word, this is in limiting equilibrium because this is F max. F max, I should highlight it. This is F max, right? None of these are not F max. 9 is not F max. This is not the maximum. Again, this is F max. This is limiting equilibrium too. Why do I call it limiting equilibrium? It's in equilibrium, but it's about to move. The maximum friction is acting. The next moment, if I change this, my applied force by 0.1, it will start to move. So the two extremes, the 5 and the 25, the value of my applied force, this corresponds to, this is limiting equilibrium. This corresponds to, this is limiting equilibrium. Here, the object is about to move up or down. Limiting equilibrium means it's about to move, about to move. Here, it's about to move up or down. Very good, Hatvi. It's about to move up. If I change this to one more decimal place, 25.1, it will start to move up. Here, limiting equilibrium. Is it about to move up or down? Here, it's about to move. Say it, please, somebody. About to move down. Okay, so this is what you had to learn today. I usually spend a lot of time explaining that because I could have just done it by just giving you the theory. Were an object kept on this thing, the maximum, the smallest and the largest force that needs to be applied is this and this, like that. But you wouldn't understand how that is. I hope you understood now what is happening here and why there is a range of values that you can apply onto an object that is kept on a slant surface to keep it still. Okay, so if I just give you the two extremes, the smallest force, so there is a smallest and there is a largest. Smallest external force that you need to give, and there is a largest external force that you can give. Smallest is when here's W sine theta, here's your F max, here's your applied force, let me call it P. Smallest force is when F max is acting in the same direction as your force. So F max is doing part of the job, so you don't have to give as much. That's why this is the smallest now. The largest force is when you have W sine theta, you have P. Remember, this P is not the same. One value here, different value here. And F max is now acting downwards. So now you have to have a large force to counteract F max as well. Here, F max was helping you. Now you have to balance F max as well. Here you are balancing W sine theta along with F max, with the help of F max. So this is a small force, that's a large force. So in both here W sine theta is balanced by your force and F max. Here you have to balance both of them. So this is a large value, this is a small value. Okay, This is the summary. What will be a good topic to write this little theory that we just did? This is the theory. And don't memorize these like formulas. Okay. This is smallest external force needed to keep the object at rest. Here's the largest external force needed to keep the object at rest. I will give you the note in a little bit. At rest. Tell me a good topic to put for this. Malik, Nathan,
Variation of forces applied on the object.
say it again.
Variation of forces applied on an object.
I like it. Variation of forces. Variation of forces applied on an object. I like it. I like the word variation. Let's polish it. Let's somebody else. Quick. I'm just trying to make this a creative endeavor. One more person. Determining range of side. Nathan, yeah, you go ahead.
No, miss, you go ahead.
Hatfi says determining range of forces applied to keep an object without moving. Yeah, that is good. I like that too. We'll say the range of, so I'll use something that you both said to come up with a topic. We can say I'll use the Nathan's word variation. Variation of, Mia says force applied to move an object. No, this is not about a force being applied to move it. This is about a force applied to keep it not moving, to keep it still. What's the job of this P? This P, what's the purpose of this P? To keep the object at rest, not to move it. If you want to move it, you just push it upward. I mean, this is what exact amount should you put on this exert on this object to keep it still. Okay, so we have Mali says relationship of forces in equilibrium. He'll say force applied to keep an object at rest. Right. Yeah, Nathan, you were going to say?
I was gonna use equilibrium, but it has already been taken, so no need.
Yeah, throughout now both these scenarios, the object is in equilibrium. Forces are in equilibrium. Forces are balanced, and there is a range of ways in which you can do it. Now we considered some cases here, right? All these, they are all equilibrium, right? The only fixed force was the component of the weight. Your external force was changing, accordingly friction was changing. So okay, let's say I want to so I will take all of your suggestions into consideration. Mihir says Malit's one is good. Relationship of forces in equilibrium. This is only about an object kept on a slope. Okay, this happens for an object kept on a slope. We'll write. Okay, let's write. I will tell you the. We'll write. So write this is the note. Here's the topic. Variation of the external force needed to keep an object at rest on a slope. It's a long topic.
Miss, would this have also been a good topic?
Yes,
Variation of forces to maintain equilibrium.
equilibrium. Yeah, I like that. Yeah, maintain equilibrium. I like that too. Maintain equilibrium on a slope. You have to
On,
have on a
on,
slope.
on a slope. Okay.
Yeah, that would have been nice too. If anyone wants, you can write that. And we are looking at the variation of the external force. We are looking at how P will vary. Okay, the largest P, the smallest P. You have questions where they ask you to compute the largest and the smallest. So I'm not going to give you like a huge note. I will give you this particular this summary of it. Okay, let's draw together. I will draw. You draw with me. That's my. This is okay. Um, I hope you are drawing with me. So in the first diagram, I'm showing you how the forces would be when the smallest external force is needed. And I will use different colors for the forces. I am only showing you the horizontal forces. Here's the external force. Here's friction. Here, the object is in limiting equilibrium and is about to move down. About to move down. W sine theta is equal to P plus F max. Therefore, P is here. P is equal to W sine theta minus F max. This P is the minimum external force, minimum external force needed to let's use Nathan's words, to maintain equilibrium. And here we mean by equilibrium to keep it at rest, okay? And then in the other column, sorry, I will keep this for you to copy before I go to the other side. So here P is, right? This is P min. I'll say P min. Can I start like that? If I keep, do you see? Okay. On the other side, it's largest external force. That is when again you have your component of the weight, W sine theta. And now F max is this way. And your force, this is the largest force. Here too, the object is in limiting equilibrium and is about to move up. How do we know about to move down and about to move up? That's by looking at the direction of friction. Here friction is acting up means it's trying to move down. Here friction is acting down because it's trying to move up. It's about to move up, about to go up. Okay. And but forces are balanced. So here W sine theta plus F max is equal to P. Therefore P max, this is the maximum P. P max is W sine theta plus F max. This P is the maximum external force needed to maintain equilibrium. Let me know when you're done copying and let me know if I need to move this up or down. Okay. And take like a 2 minutes break. 2 minutes break to digest this. 2 or 3 minutes. 2 or 3 minutes. Okay. Don't go anywhere. Stay in your seats. Drink some water. Okay, everyone. So hope this was clear to you. We will now look at a question related to this thing. Okay. So here's the question. I'm taking it from your book. This is okay. First, yeah, I will show you the question. If you have your books, you can look at your own books. This is the last exercise in your friction topic in the book. Last exercise, last question, number 17. We have to do 16 as well. We did up to 15. But first, I want you to try number 17. So quickly copy the, if you have the book, you can just refer to your book, but you have to copy the diagram anyway. Quickly copy the diagram and let's tackle this question.
Miss, page number 107, yes?
That's correct. Yeah, but your books, if your book is different to mine, it will not be the same page. If I give you the exercise number, this is end of chapter review exercise 4. Okay, let's read the question. The diagram shows a particle of mass 0.6 kg on a plane inclined at 25 degrees to the horizontal. The particle is acted on by a force of magnitude P directed up the plane parallel to a line of greatest slope. So the external force applied on the particle is P up the slope. The coefficient of friction between the particle and the plane is 0.36. Given that the particle is in equilibrium, find the set of possible values of P. Find the set of possible values of P. So if you can find the smallest value and the largest value, you know that your P can be in between those two values. Any value between those two. So it's a matter of finding the smallest P possible and the largest P possible. Okay, so this is directly related to what we just discussed. So can you start? You start, okay? Can I take the book away? Can I take the book away? Or are you, anyone copying the question? Okay. If you're hearing other voices in the house, you let me know. Okay, I can ask them to keep their voices down. So this is question number 17. This is from the textbook, page 107, according to my book. Okay, we might have different versions, different editions. Let's draw it. This is 25. Here's your object. Mass is, M is 0.6 kg. Mu is 0.36. That's all we have. So you have weight acting down, 6 newtons, right? mg. So I can replace that with the two components. This is 6, because this 25 will come here. So 6 cos 25 and 6 sine 25. And remember, when you have marked them, you don't need this anymore. Okay. And then you have your P acting upwards. And if I, just for the completion of the full body force diagram, you have R as well. This is in equilibrium. So vertically, do you see when I say vertically, the direction I'm showing? When I say vertically here, it is with respect to the slope. Relative to the slope, this is the vertical. Relative to the slope, this is the horizontal. Okay. So vertically R and this will be balanced. We know that. And then this way also balanced. So okay, where is friction? So we need to draw two diagrams, one corresponding to the largest P, one corresponding to the smallest P. If this is when P is at its lowest, okay, then F max is the only force that would be different here.
F max acts upwards.
F max up. F max, very good, acts upwards. Okay. Remember, F max is equal to mu R. Now you need to find R. So if you consider vertical this way equilibrium, Vertical equilibrium, R is equal to 6 cos 25. You can find that value or leave it like that. And then horizontal equilibrium. So I'm just trying to find the value of P. That's my aim here. And that P would be the smallest P. Horizontally, I know that 6 sine 25 is equal to P plus F max. I want to find P. P is equal to 6 sine 25 minus F max. That is 6 sine 25. F max is mu r. Mu r. I can put r from here. 6 sine 25 minus mu 6 cos 25. I know mu as well. Mu is 0.36. I could have put 0.36 here. Oh, my document is stuck. Now, if you put all your values, mu is 0.36. Tell me what that is. What you're getting is P min. Okay. And then you would do another one when P is at its largest. I know you can't see what I'm writing. Okay. Somebody has to tell me the answer to this. Okay. Then when P is at its largest, you draw this again.
Miss,
Yeah.
I got the answers 0.58.
Very good. Can you give it to 3 decimal places?
Okay, 0.578.
Very good. When P is at its largest, you have your two components of weight, 6 sine 25, 6 cos 25 are acting up, P still acting that way, and now your friction would be down, F max. Or vertical equilibrium, nothing has changed. You can use the same thing from the previous. Now horizontal equilibrium, we have 6 sine 25 plus F max is equal to P. Therefore, P is equal to 6 sine 25 plus mu R is 6 cos 25. How much is that? So that's going to be your P max.
Miss, the answer is 4.49.
Very good. Very good. Now, the question was, find the set of possible values of P. So you finally write, therefore, P can be between 0.578, can be equal to that, or less than 4.49. Is that clear? Any questions?